Hi, welcome back. This is a brief video to discuss the 15% rule and how to use it in a practical way. It's really important to understand what the 15% rule is because it can do a great deal for us and it can save the patient a great deal of dose if used properly. So let's just discuss this in a nutshell. What is the 15% rule? The 15% rule basically states that if you increase your KVP by either 15% going up or 15% going down, it's the equivalent to either doubling your mass or cutting your mass in half. So let's look at this from a practical standpoint. If you used 70 KVP and you also used 20 mass for a particular examination, let's say in this case, abdomen. And the problem with this was your exposure was just a little on the underexposed side, enough so that you had to actually repeat the exam. You could go back and double your mass to 40 mass, leave your KVP exactly where it was, and you would probably solve the problem quite well. You'd have a beautiful image, but you'd also have a patient who received twice as much. Actually, a lot more than that, because you've already exposed them once, then you expose them again, but this time with the mass being doubled to 40. That's a lot of exposure to think about. So the 15% rule allows us to solve this problem in a different way. And how we could do that would be for us to continue to use 20 mass, but instead of using 70 kVp, we increase the kVp by 15%. That's roughly 10 or 11 kVp, right around there. Let's just say 10 to keep this simple. So instead of using 70 kVp for the repeat, we increase it by 15% to 80 kVp because we know this increase of 15% is the equivalent of doubling this mass to 40. But in fact, we don't have to. We can leave the mass right where it's at 20 mass, increase the KVP by 15%, and when we go back and repeat that image, we will have solved our problem. It will no longer be underexposed. Why is this? Well, the first one we did at 70 kVp had a certain amount of energy that drove those photons through the patient's tissues. Okay? Some of them got absorbed along the way. Let's just make this our patient right here. So, as that X-ray photon traversed through the patient, okay, some of those photons got absorbed in the patient's body, and then some of them made it out the other side to strike the image receptor. Okay? When we increase our KVP to 80 KVP, the energy of the beam increases and it looks something like this. More energetic. Same velocity, keep that in mind, it's important. Same velocity, speed of light. That never changes with X-rays. Never, ever, ever. Whether you have a super low KVP or a really high KVP. All those X-rays are going to be moving with the same velocity. They're moving at the speed of light or they don't exist. What's changing is the characteristics of those photons, how energetic they are, what they're able to do for you. And in this case, we're talking about penetrate or attenuate penetrate with less attenuation through the tissues. Okay? So let's continue with our little picture and see if it makes sense. So once we've increased the KVP by 15%, we have a more energetic beam overall. What that's going to allow to happen is, let's just draw our patient tissues again. We're going to have fewer photons being absorbed in the body and more photons making it all the way out the other side. So we have more photons reaching the image receptor, which is what we needed all along. The image receptor was underexposed. So we could have solved it by, of course, doubling our mass from 20 to 40 and basically used the same energy of a beam to put more photons through the patient, and that would have resulted in more photons hitting the image receptor, but the patient would have received those photons as well. So what we can do by increasing the kVp, it's kind of like you're making better use of the photons you already have. Instead of increasing the number of photons, you are using them in a more efficient way. You're sending more of them through the patient all the way to the IR. And you're getting a great image by increasing your kVp by 15% rather than doubling the number of photons. Okay? So I've got a lot of markers now.